Hello and welcome to The Daily Space. I am your host, Dr. Pamela Gay,
And I am your host, Beth Johnson.
and we are here to put science in your brain. As you may have caught on Tuesday, this week was the summer meeting of the American Astronomical Society. This is a smaller meeting than the winter meeting back in January, but it still rocks out a lot of science, with many teams holding their big releases for this event. For instance, the CHIME telescope collaboration shared their catalog of nearly 400 newly discovered fast radio bursts. These weird flashes in the sky were first discovered in 2007. Seeing them is hard. They only last a few milliseconds, and they're star-like in size, just a pinprick of radio light. Prior to the construction of CHIME, they were found only when folks got lucky and happened to have a radio telescope pointed in the correct direction at just the right moment. CHIME is a new kind of radio telescope, and it uses half cylinders and complex sensor arrays and even more complex software to observe vast swaths of the sky simultaneously. From its location in British Columbia, it can observe the entire northern sky every day. Since it began operations in 2018, it has quadrupled the total known number of fast radio bursts. With this kind of catalog, it begins to become possible to look for trends. Currently, fast radio bursts are divided into two groups, those that repeat and those that don't. The 18 known repeaters all appear to last slightly longer and emit light in a broader range of frequencies than their shorter, more narrow counterparts. This hints that there may actually be physical differences in the origins of these very similar millisecond-long bursts of radio light. This catalog also yields some spatial information. As the light from distant fast radio bursts travels through the universe, clouds of material disperse the radio signal and highlight locations where there's lots of material. Using CHIME's data, researchers are able to trace out the large-scale structure of our universe, one momentary flash of light at a time. The data presented at this meeting is just a start. The longer CHIME operates, the more discoveries will be made. The more researchers who get time to explore the data, the more breakthroughs in understanding will be made. We're still in the early days, and I can't wait to see what is yet to come.
While some surveys simply look to see what's there, others specifically target one kind of an object or another, and then look for trends in those objects. Using the Atacama Large Millimeter Submillimeter Array, Alma, a team of researchers led by Lucy Xeris looked at 5 planetary nebulae to see where they kept their molecules. Planetary nebulae are formed when stars like our sun die. As they run out of fuel they can use for nuclear fusion, their core collapses into a white dwarf while the outer layers are exhaled. In visible light telescopes, we see hot gas, with green coming from oxygen and red from hydrogen. We also see dark bands, where either there is no material or where there is material that is too cold to shine in visible light. With Alma, we see colors redder and cooler than what our eye can see. Instead of the light from hot atoms, Alma catches light from cool molecules, and it found that those molecules lurk in the dark places of planetary nebulae. This hints that the hot structures we're used to seeing are actually shaped by cooler, denser clouds than Alma can reveal. This work is just starting, with a handful of nebulae so far observed, but this is an important piece of the puzzle for understanding how these planetary nebulae end up with such wild shapes.
The vast distances in the universe mean a lot of things that we're interested in are too far away to readily see. Understanding the details of small, distant things is particularly hard. But scientists can often find creative solutions. When we aren't surveying vast areas of the sky, we can also sit on individual objects or regions for long periods of time to see how things change. Small variations can hint at super cool science. In more research presented at the American Astronomical Society meeting, Elena Menjevekis presents her team's observations of tiny brown dwarfs using the Keck telescope. Instead of taking images, her team spread the light of the brown dwarfs out into a spectra or rainbow and looked at the specific colors that correspond to light from different molecules. Brown dwarfs are objects big enough that they can burn heavy hydrogen in their core, but not big enough to burn regular hydrogen like a regular star. This means that they may ever so briefly act like stars before settling down to look, we think, just like gas giants. Manchevakis' team wanted to see if light from brown dwarfs varied in systematic ways that would match with changing cloud patterns. As a starting point, they looked at Betapictoris B, a brown dwarf just 115 light years away and just 12 times larger than Jupiter. With a 3.5-hour rotation pattern, it is rotating faster than Jupiter and easy to observe during an Earth night. According to the release, the light reveals clouds of hot sand grains and other exotic elements. Potassium iodide traces the object's upper atmosphere, which also includes magnesium silicate clouds. Moving down in the atmosphere is a layer of sodium iodide and magnesium silicate clouds. The final layer consists of aluminum oxide clouds. The atmosphere's total depth is 446 miles or 718 kilometers. This paints a picture of a world we can't actually see, a world with clouds and likely banding and complex chemistry. We can understand what's going on by understanding at what altitudes and what temperatures these different molecules can form, and using that to figure out what's happening at different altitudes and temperatures in this planet's atmosphere. As with so much of what we're discussing today, these are just preliminary results, and we can't wait to see what is learned as they survey more brown dwarfs for longer periods of time.
Cataloging what's out there is really one of the most powerful ways to understand our surroundings. That whole idea that science is done by making a hypothesis and then testing it, that idea ignores the fact that you really should look to see what is there first and then make a hypothesis based on those initial observations that can be tested with future work. While CHIME is tuned to look for radio bursts, other surveys look in other colors and in other ways. The orbiting Gaia Space Telescope is measuring the brightness, location, and movement of large chunks of our Milky Way galaxy, and this work makes it possible to see how some stars are simply passing in their very different orbits, while others seem to originate from the same family of stars. Continuing the Sloan Digital Sky Survey's tradition of announcing new stellar streams at the American Astronomical Society meeting, researchers using Gaia announced that an object loved by many amateur astronomers, the Southern Beehive Cluster, or NGC 2516, is much bigger than what we see in our binoculars. The full system is at least 1,600 light years tip to tip, and at its distance is able to sweep across 40 full moon widths of the sky. Research co-author Gaspar Bacos explains, I have seen the Southern Beehive many times through a pair of binoculars under the dark skies of Chile. The cluster nicely fits the view of the binoculars because its apparent size in the sky is something like the tip of my thumb at arm's length. It is curious to know that the cluster actually spans an area as big as my entire palm held toward the sky. Lead author on this study, Luke Buma, points out that the broader implication is that there are bound to be other enormous open clusters like this. The visible part of the cluster, where we can easily see the stars close together, may be only a small part of a much larger stream. Stars that all belong to the same cluster also have the same age and same chemical composition. The more stars we know belong to one system, the more opportunities we have to see how solar systems can form when chemistry is held constant. We'll be talking more about why that matters after the break. Stay tuned.
One of the coolest things to see at the AAS was the abundance of young researchers leading the charge in understanding exoplanets, planets orbiting stars in alien solar systems. First confirmed in 1995, exoplanets weren't something a lot of us older folks were ready to focus our career on when we got started. Now there's just so much data and so many opportunities that researchers are diving in and essentially homesteading on their own awesome research topics as the field comes into its own. Part of what transformed exoplanet research from a low data, high risk research field into the rich topic that it is today is the success of the Kepler Space Telescope. This mission was originally launched to focus on one small field of stars that it observed over and over for years as researchers waited for planets to transit in front of those stars and reveal themselves. Over several years, Kepler found star after star after star with planets passing in front of them. Then its navigation system went blank, and the research it had been doing was no longer quite possible. But as we keep saying, researchers will get creative when they want data. While they couldn't use Kepler as planned, they could use it to look at a series of fields spread around the sky that were positioned in places the telescope could still point. This redo was called K2 and yielded its own rich harvest of planetary discoveries. The first planets discovered and studied in this data were the ones that were obvious. But as the years have passed, the software has improved, and it's become easier to find the less obvious planets trying to sneak past their stars without being seen. In fact, the sample was increased by roughly a third, with a much larger sample set for both the original Kepler data and the extended K2 mission. Now, with this software-enabled new trove of planets, it's become possible to look at things in a statistically rigorous way. And it turns out, when you look closely, the stars in the two populations aren't identical. The original mission looked at stars that largely live in a region of the galaxy where most of them have a composition similar to our own sun. In the follow-up, they looked where the spacecraft could look and tended to examine stars that, because of where they were, just happened to have fewer heavy atoms and less of the stuff we think of when we think about building planets like Earth. Interestingly, although maybe not surprisingly, researchers found that the planets that formed, well, or sometimes didn't form in systems with fewer heavy atoms, well, those systems with fewer heavy atoms, they just had fewer planets. Now, beyond this, they were also able to look at what kinds of planets form in what kinds of systems. This was done with the initial Kepler data, and they discovered that there is this place in solar systems that is extremely hot where larger planets just can't exist. This is the sub-Neptune Desert. They also find that there's this strange gap in radius in planets where you just don't see things of a certain size no matter where you look. Now, the question became, is this a function of the composition of stuff available to form planets, or is this universal? Looking at the K2 data, they found there was a slightly different distribution than what was found, but that sub-Neptune desert, still there. That gap in radius, still there. This means that there's something going on during both the process of forming planets and perhaps during the evolution of planets later that either prevents the formation of worlds of these sizes and places or destroys them. As we talked about earlier this year, people are now starting to ask, if you start with a Neptune-like planet and you put it too close to its star, does that atmosphere get blasted away, leaving behind, well, a giant earthy rock? Time will tell. But now we have a whole lot more planets to yield up their story. Now, after the break, we're going to be back to talk to you about a moon that is bigger than a planet and has just been observed by Juno Cam. Stay tuned.
A few days ago, we brought you the news that NASA's Juno spacecraft was scheduled to perform a flyby of Jupiter's moon, Ganymede. This flyby would capture the first close up images of the large moon in 20 years. And we are pleased to say that the flyby happened, and 2 images have already been released. The 2 images show amazing detail as they were taken from a distance of about 1,000 kilometers. We'll have both images on our website, dailyspace.org, for you to peruse at your leisure. Enjoy the craters, the possible tectonic faults, and the patches of bright and dark material. One of these images was taken by the Juno Cam imager, and the second was taken with the Stellar Reference Unit STAR camera. That second camera is the same one that helped scientists figure out that Earth's zodiacal light phenomenon was caused by meteorite dust from Mars. Today, we are pleased to have with us Dr. Candice Hansen, a senior scientist at the Planetary Science Institute and a co-investigator for the Juno mission. Dr. Hansen is also responsible for JunoCam operations, and she is here today to talk about this flyby, upcoming flybys, and the citizen science aspect of JunoCam. Thank you for joining us today, Dr. Hansen, and welcome.
Yeah, thank you for inviting me.
So, how did you get involved with Juno? What was the process to work on this particular mission?
Back in the days of when we wrote the proposal for the mission to NASA, Scott Bolton approached me about being responsible for lining up an outreach camera, getting one purchased actually and built and now operated. And we're so excited. We're so proud of our little outreach camera because it's really doing great science too.
So what does your everyday look like in operations for that side of things?
Well, Juno is in a 53-day orbit. So there's a time that's spent planning for the upcoming flyby because we get very close and we take images for just a few hours. And then the spacecraft gets further away and we have some downtime for the camera anyway. So we spend our downtime looking at our data, looking at our citizen scientist contributions, and then looking ahead to the next flyby and planning what images will we take on the next pass, and just really enjoying being a part of this mission.
So this is part of Juno's extended mission, these new flybys. So how did this Ganymede flyby come about? What was the process to plan this?
This is a very interesting situation because when we decided to stay in the 53-day orbit, it also became the case that we would have Jupiter's gravity, the nature of Jupiter itself would slowly affect the orientation of the orbit. And so up until now, we have not gotten close to any of the Galilean moons. But because of the way the orbit has evolved, we are now starting to cross their orbital paths. We actually passed Callisto already, but we weren't anywhere close to it, or better said, it wasn't close to us. But this time, we were able to get within 1,000 kilometers of Ganymede. And knowing that was coming up was very exciting. Our mission goals have a lot to do with Jupiter's magnetosphere and atmosphere and the gravity field. And so our instruments to focus on a moon is really new science for all of us. And I might add very exciting science because Ganymede is a moon with its own magnetosphere. So the spacecraft is very well interested for studying that. On the JunoCam, from the JunoCam perspective, these are the first close-up images in the decades since Galileo and since Voyager. And it turns out that where the patch of Ganymede that we flew over, that we got pictures of, was imaged best by Voyager, not Galileo.
Oh.
So, yeah, so we're really looking at differences over 40 years. And
Wow.
as fabulous as I think the Voyager images are, I worked for the Voyager imaging team at the time we took those images, to compare the output from a modern camera, a modern detector, getting so close, as close as we did. It just, the quality of the images is really, a little sad to say, outshines Voyager.
So, you sound so excited, and I share your enthusiasm so much. So I'm really thrilled about all of this. Are there more flybys being planned that are in the offing for Juno?
Yes, next year we will, our orbit path, well, we have one more distant Ganymede. We will fly by Ganymede again next month at a distance of about 49,000 kilometers. This flyby was at 1,000-kilometer altitude. So we have one more relatively distant flyby of Ganymede. And then about a year from now, we will make a close pass by Europa. And then another year later, we'll be getting close to Io. And that's because we are, as I said, counting on the evolution of the orbit to take us in to where we're crossing the orbits of the moons with the orbit of Juno.
Oh, that is really exciting. Which one? I hate to. It's like asking about your favorite kid, but which one are you most excited about? Ganymede, Europa, or Io?
Oh, I have to say Ganymede because that's where we've just been. Next year, my answer will be Europa.
There you go. Now, see, that is a very, very sensitive answer. I like that.
No, Ganymede's actually always been my favorite. Now I have to confess.
So, what are we planning on learning using these GenoCam images? So we're going to go back and we're going to compare to Voyager and maybe even to some Galileo images, and see.
Mostly Voyager. It'll be mostly Voyager, at least for Ganymede. It's definitely was best imaged by Voyager. Well, one of the things that we're realizing is that the map of Ganymede, which is put together by the U.S. Geological Survey, was actually not as good as we thought it was. We're finding that even though the resolution was comparable, a number of the Voyager images were a bit smeared due to the spacecraft motion. And so we are going to really fill in a lot of gaps in that map. And so we'll be able to we'll have a better count of craters of specific sizes and better idea of the orientation of the groove terrain and things like that. So we're just really going to have some substantial improvements in that map.
Oh, that's really exciting. Okay, so I know there's a citizen science aspect to Juno and GenoCam, and we're going to talk about that in just a minute. We're going to take a quick break, one last break, and then we'll be right back with Dr. Hansen. Stay tuned. And we're back with Dr. Hansen. Now, once again, we have a lot of people who enjoy science, doing science, and are not professional scientists. And you have mentioned to me, and I've seen that GenoCam has a citizen science project available. So will you tell us more about that and how people can participate?
Yes. The primary reason for GenoCam to be on the Juno payload, in fact, was to give the public, anyone interested, everyone interested, an opportunity to be a part of a mission, a flight mission. And so we set up our sort of introductory web page to lay out the 5 things that a more traditional imaging team would do. And so you can go there and check out any one of those 5 places to see what you might be interested in. Most people like the image processing page. So if we can show that one with the galleries,
Yep.
there are 3 galleries. The top one are the JunoCam images themselves. So when we get the images back from the spacecraft, they go through a pipeline of processing, and then we post them on our website. So depending on the downlink schedule from the Deep Space Network and things like that, it may be a couple of days, but pretty much within a few days, we have our images posted. And so we have a completely raw version because there are some people who like to start with that. And then we have what I call the lightly processed versions. And most people start with the map projected color reconstruction and then move on to doing whatever they want. And we don't dictate. We don't say what people should do. We love the creativity of what people do with our images. I have to say, I so enjoy looking at what people do. And so the middle gallery is featured submissions, and then the lower one is all of the contributions that we've gotten, which are in the multiple thousands. So focusing, though, on the featured submissions gallery, there is such a wide range of what people like to do with the images. We have one contributor who really does his best to recreate the exact color of Jupiter as you would see it if you were riding along on the spacecraft. And it's a very pale pastel kind of palette. But most people love to exaggerate the color, enhance the color. They zoom in on features of interest. And I think my most favorite and actually least expected aspect is the artists. We have had a number of artists that start with our images and then make fabulously beautiful creations, worthy of hanging on your wall art, whimsical contributions, cartoons. I mean, it's really quite the gamut, and it's all good. It's all good. We all, I think, learn from seeing Jupiter through each other's eyes. And I have to say, it's really changed my perspective as a scientist. What I've realized is that the enhanced and exaggerated color really helps my eye-brain combo to zoom in on interesting features. And then I go back to the raw data and I ask myself, is it really even there? And sure enough, usually it is. It's just, so pastel that it didn't jump out, and it wasn't noticeable. So it's all good.
It looks like a lot of fun to play with, and I am definitely excited to have our members, our community, come and play with all of your stuff too. So I am looking forward. If anybody processes images in our community, please let us know. Share them on Twitter, share them on Facebook, link to us, and make sure, of course, you upload them to JunoCam's website so that Candice can see them too, and then we can all enjoy all of the fabulous art and all of the amazing Jupiter images out there, and soon more Ganymede and eventually Europa and Io images. And I will tell you right now, I am not an image processing person, but when these Io images come down, I'm going to play because I am really excited about seeing Io through some better cameras and, not distant Hubble images of a faint blob with some very vague lava fountaining going on. So I am definitely going to play with these. So Dr. Hansen, thank you so much for coming and talking to us today. We will have links to the JunoCam Citizen Science pages on our website, dailyspace.org. So they will be there for you to take a look at. And I am really excited. So everybody stay tuned and follow this mission, and we'll bring you everything we can as it's updated. But for now, this has been the Daily Space.